Hi everybody, welcome back to another tutorial. I got a question, a very quick question from one of the subscribers asking, well, simply he's saying, why do we need to know the zero moment location on a beam? In other words, let's just say if I have a moment diagram that looks probably something like this, and I have a support here, for example, and another support here, and let's say I have a shear diagram, probably, I don't know, maybe it looks something like this, I don't care, okay? But the question was, we know for sure that sometimes we need this x, the location of the zero shear, because that corresponds to the maximum moment. But why do we care about where the moment is zero on a beam? Well, that's the first part of his question. The second part is there an easy way to find it, or a quick way to find it? Okay, so I think the best way to answer this question is by doing an example. Okay, and let me try to select this and start all over again. Okay, now we have a clean sheet, so let's do that. Suppose I have a beam, it's a simple beam with an overhanging part, and I have the loads, or the distributed load, like this. The dimensions I have are the load here is 10 kilonewtons per meter, and this length is 10 meter, and this length is 2 meters only. And I need to find the, okay, let's do it this way. So find x such that m equals to 0. And the second question is, why do we need to find it? I'll leave the why part until the end, after we understand the technique of how to find it. So basically what we do is draw the M diagram. Easy said, but we will go through the whole procedure again. That is finding the reactions, drawing the shear, and drawing the moment diagram. Okay, so let's say I have this is point A and this is point B, and the reactions here are AY and BY. Okay, so where do we start? We start with the summation of the forces in the Y direction, and they should equal to 0. So if I concentrate the load of the 10, it should be concentrated in the middle, and the middle is, probably that doesn't look like a middle, but anyways, you get the idea. The middle part is half of the whole beam, which is 6, so the distance is, let's say it's 6 meters. And the value of this load should be 10 times the 12, which will give me 120 kilonewtons. So I have AY plus BY, these are the reactions, should be equal to the load from the top, which is 120 kilonewtons. Okay, now we'll take the summation of the moments about a point A, let's say equal to 0, and I will set the counterclockwise to be the positive direction. So what do I have? I'm gonna have BY multiplied by 10, so it's 10 BY, and the rotation is positive. Then I'm gonna have 120 multiplied by 6, so it's 120 multiplied by 6, and the rotation of this is going to be in this way, so it's a negative. And that's it. Basically, I should set this equal to 0, and if I solve for By, I should get value of 72 kilonewtons. Okay? Now from this By, I can get Ay, because I know that Ay plus By from this equation, which is a 72 here, should equal 120, and that will lead me to a value of Ay, which is equal to 48 kilonewtons. And we've done the solution of we've done these kind of problems a couple of times now. I think you guys are experts in finding reactions. Okay, so let's move on. Let me push this up. Okay, and now what do I have? I have reactions. I basically should start drawing the shear and bending moment diagram. So let me draw the beam again. And this is the distributed load with 10 kilonewton, and I have 10 meters and 2 meters. Okay, and I have a reaction here, Ay, which is 48. I will lose the units for now. And here we have 72. Okay, and just to be nice and neat, let me draw a straight line like that. And here, and this one. Then I'm going to draw a line like this, and a line like that. Okay, now we're ready to start drawing the shear diagram to start with. So this is the V diagram. I'm sorry, let me correct this. This is the V diagram, and this should be the M diagram. So basically what we are doing, we start with from this point and we go up 48, which is the value of the reaction. Then we have this 10 kilonewton per meter, and what basically says that if you are at 48, if you move 1 foot to the right, you're gonna drop by 10. You move another foot, you drop by another 10, and so on. So with a quick calculation, I can find the point here, which is basically 48 dropping 10 over 10, or basically saying that this point right here will have a value of 52. Okay, and just quick reminder, so I'm starting 48 and I am dropping 10 kilonewtons for a distance of 10 feet. That should give me a minus 52, and that's the minus sign here. Okay, now what happens? Now I have the 52 right here being pushed by a value of 72, so I'm gonna reach a point here which is 20. The reason it's 20 because if you add 72 to the minus 52, you will get a 20. And lastly, of course, at the cantilever end, it's going to be a 0, so it should look something like this. Okay, so basically that's the shear diagram. Let me go ahead and push this thing a little bit more so I have more room for the moment diagram. Okay, and for the moment diagram I'm gonna redraw the lines again. Maybe I'm gonna erase this thing right like this, and let me draw the lines again starting from here, that, and this one, and that one. and like that. Now I have another point I have to take care of, which is this point right here. And if you remember this point right here, this point is the 0 V, which is the maximum moment diagram. Okay, so let's do this in purple, and let's do this line like that. Okay, so what is the value here? Basically the value of this moment is the area under this curve, and the area under this curve is 1/2 multiplied by 48 multiplied by, oh okay, now I got stuck because I don't know this distance x, so I need to find this distance x, and the easy way to find it is doing the similar triangles, and the similar triangles are this part and that one, and the easy way to visualize it is by doing this. It's basically the same triangle, so I have a triangle here and a big triangle like that. Okay, so let me draw the triangles like that. Now, what is this distance? This is 48, and this one is x. This thing is the whole length 10, and the whole length here is 48 plus the 52. The 52 is this distance, and now I'm going to take the positive values because I'm talking about distances, so the total length is 100. Now, and let me just make some room here. Okay, now from similar triangles I can do, basically I can do either way. Okay, so I can go x over 10, the base over the base, the height over the height, the base of the small over the base of the big, the height of the small over the height of the big triangle. So from that I get x equals 4.8 meters. So now I can find the area here. Since x is 4.8 meter, the area again is 1/2 multiplied by 4.8 multiplied by 48, and that should give me 115.2 kilonewtons meter. Okay, so I have a value here of 115.2. I'm gonna lose the units again. Alright, so is it a straight line? Is it a curve? Since the shear diagram is a straight line declining, then this should be a parabola or curve. If the shear diagram was a straight line, a horizontal straight line, then the moment diagram here is going to be a straight line. Basically what I'm saying here, that if the shear is from, ask yourself this question: what is the degree of this line? This is a line from the first degree, so the shear diagram should be for the second degree. And if it's a straight line horizontally, that's of 0 degree, and then the moment diagram should be from the first degree. Okay, now what about the moment at this point? Okay, basically I'll add the area of this triangle to the previous point or to the previous moment. So what is the area of this triangle? I'm going to do it over here. It's 1/2 multiplied by 52 multiplied by this distance. This distance is whatever is left after I calculate the 4.8. I subtract it from the 10. And when I subtract it from the 10, I'll get 5.2, and that should get me a value of okay, let me see here, but I have to do 115 plus, and this value should be negative. 5.2. So I'm adding the moment, the previous moment, and I'm not losing the signs here because this is a negative 52. Okay, and if I do this, I'll get minus 20. So here it's minus 20. So I should get something like this. Oh, I'm sorry, this is way off. And let me undo this one. So I'll try my best to draw it. Should look something like this. Okay. Now, if you're confused about this 20, the moment at this point, it's either the summation of the areas before or the summation of the areas after. So what is the area of this triangle? Okay, the area of this triangle is 1/2 multiplied by 20 multiplied by 2, and that should give me a 20. Okay, now what is the moment here? 0, and it's concave like that. And you can go back to one of the videos explaining the concavity and stuff. Okay, now the question was, what is the importance of this point, and how do I find it? I need this distance x. Okay, now let's try to think about it for a second. Let me push this. Okay. All right. The point here is a 0 moment. And from before we've seen, I'm sorry, let me get this graph again. And from the shear diagram, we've seen that the maximum moment corresponds to the 0 shear. So if I have a positive here and I calculate the area, I'll get the maximum value. Now the trick behind it, or the way to think about it, what negative area should I add to this positive area to make the summation equal to 0? This way, if I can find the negative area, I can find this x. How so? If I add the positive area to the negative area and they are equal in magnitude, I'll get 0 moment. And this 0 moment should happen at a distance x. So, for example, let's assume that this area, for example, has a magnitude equal to this whole area. Just for an assumption. If that's true, then up to this point and from the left, this is the distance x I'm looking for. So now I have a shear diagram that if I can find the area, or in other words, this distance, this small distance, and then I calculate the area and find it equal to the previous area, then I'll be able to say that whatever is before equals to whatever is after, so the summation should be 0 here for the moments. Then this distance x, or this point, has the 0 moment. Let's try to do it. Maybe it will become clear for you guys. Okay, let me scroll this thing up a little bit more. So what I'm saying is, if I have, this is the shear diagram I am having right now. Okay, this is the shear diagram for this segment. And I know that this area, let's say area 1, should be equal to some area included in this triangle, let's call it area 2, such that this distance all the way here should give me the x value for m equals to 0. Now all I need to know is how to find this distance. Think about it for a second. This area has a base of 4.8 and a height of 48. The second area, the big one I mean, has a base of 5.2 and a height of 52. I don't know, guys, if you agree with me, but it's very obvious that if I want the area of this triangle to be equal to the area of this triangle, why not make this unknown distance equal to this? So I have exactly similar triangles, but this one is flipped. So this unknown distance is 4.8. And if I do this, 4.8, it's the same base. And since it's a straight line, a constant slope, the value here is going to be 48. So obviously the area here equals this area. Okay, one more time. The area of this triangle should equal to a certain area of another triangle here. The base of this triangle is 4.8. So by inspection, if I make the base of the other triangle 4.8, and I'm capable of doing that because the 4.8 is less than the big base here. So I can select an interior triangle, make it with a base 4.8, and since this line has a constant slope, this point is a negative 48, which is equal in depth at least the height of this triangle. At the end I'll have a triangle here that is exactly the same area, the same everything for this upper one, except it's flipped. So the distance where the zero moment takes place, it's from the beginning all to here. So it's basically 4.8 plus this 4.8, it's 9.6 meters. Alright, so we found the distance where the moment is 0. Now, why do we need this? The best example I can think of right now on the top of my head is when we are doing reinforced concrete. For example, the location of the rebar. So let's say we have a beam. I'm looking at the beam sideways, okay, and I'm having some rebars reinforcement at the bottom, and the reason we put the reinforcement at the bottom is the tension side is here, because you know, guys, concrete is good in taking compression, but it's weak in tension. That's why we add reinforcement in the first place. So since there is tension here and there is compression on top, we need some reinforcement in the bottom. And if this is a beam, the moment diagram for a simply supported beam with a uniformly distributed load looks like this. So look at the moment of this beam, it's all positive. Now, what if, let me try to remove this and start this thing. Cut. Okay, what if you have a beam that is cantilever and it's a concrete beam? I won't put the reinforcement here. So the moment diagram for this looks something like this. So it's negative. From that, I conclude that the tension, if this is the beam, the tension happens on the top fiber. So basically the top fiber trying to open up and the bottom fiber trying to get together. That's the easy way of thinking about it. So what I need to hold the top fiber together, so I need to put some reinforcements on top. So now you know if the beam experiences negative moment, according to our sign convention, the reinforcement should be on top, and if the beam experiences positive moment, the reinforcement should be in the bottom. Now let's mix and match. Let me delete this. Our case, or the example we had a moment diagram that looks like this, right? So should I put the reinforcement on top or should I put them in the bottom? Okay, well, for non-engineers they would say, okay, just go ahead, put some on top and put some on bottom, that's it. But engineering is all about making it practical and economical, right? So the section that I'm interested in should have some reinforcements in the bottom and some reinforcements in the top. Without going into so much details of how to select the sections or how to distribute them, think of it this way. What if I told you that whenever you see a positive moment, put bottom reinforcements, and whenever you see negative moments, put top reinforcements? The very first question you're going to ask yourself, okay, so where should I put the positive and where should I put the negative? So you need to know when the beam experiences the positive moment and when it experiences the negative moment, and that all of these pieces of information you can get from the bending moment diagram. Now, looking at the bending moment diagram, I see this point right here. Whatever is before this point is positive, and whatever is after this point is negative. So if I don't know anything about designing reinforced concrete, I'm gonna say, okay, maybe I don't need these kind of reinforcements here, and I don't need this kind of reinforcement here, because according to the logic we discussed, I put the bottom under the positive and I put the top under the negative. So that's one of the reasons you need to know where the negative moment starts and where it ends, and the same thing goes for the positive moment. I mean, there are a lot of other reasons, but this is the most common reason, that probably the very first reason people are gonna discuss if you ask this question. Okay, now the thing is there an easy way or a hard way to find the location of the moment where it is equal to 0? Well, there are two ways. To be honest, I cannot think of another way for now, but there is the long way and there is the short way, but each way has its own advantages and disadvantages. The short way is the one I just showed you, going through the problem very quickly, finding the reactions, finding the shear, and drawing the moment diagram, and understanding that at a certain point, whatever on the shear diagram, if you equate the areas before the zero shear point and after the zero shear point, and equate these areas and realize that you need similar areas to come up with the X. That's the short way. The other way is basically finding the equation of the moment diagram, and of course finding the shear and moment diagram equations. Then basically what you need to do is just set the moment equation equal to 0 and solve for X. Okay, now let's do one more example that is a little bit challenging than this, and let's see how can we solve for the shear and shear force and bending moment diagrams, and from that we can get the zero location, or the zero moment location. So let's start a new document. I don't need this anymore, thank you. So let's see. I'm having a beam. It's a little bit challenging beam. Not that challenging, but I mean, you guys, I think you know how to do most of the problems by now. If I have support here, and I have 10 kilonewtons here. I think I need to minimize this. And I have a distributed load that goes like this. And I have a force here which is 20 kilonewton. Okay, and the distances are here, we have here, like that, like that. We have all the distances are in meters, so it's 2, 3, 2, 2, 2, and all of them are in meters. And the load here is 5 kilonewton per meter. For this example, I won't go through the finding the reaction. I'll leave that as an exercise for you guys. But if I call these points to be A, B, C, D, E, and F, I will find the following. EY should equal to 28.9 kilonewtons, and BY should equal to 26.07 kilonewtons. So you guys do the reactions and check your answers with these numbers. Alright, now let's do the shear diagram first. So the shear diagram should look something like, and these are the points I am interested in: this point, that point, that point, and this one, and that one. Alright, so the shear diagram should look something like that. Okay, what is the shear value here? It's a free end, so shear value here is 0. Let me change the color. Okay. What is the shear value here at point B? Basically, the shear value here is the area of this segment. The height is 5 and the distance is 2, and the shear value should be 10. But this portion is trying to get me downward by a value of 5 for each meter. So I'm here I'm at 0. If I move 1, I'll get to 5 with a negative. If I move to 2, I'll get to negative 10. Alright, so Here is the by, so the by will try to push me up, and if it does, I'll get to the point 16.07. And again, this portion is trying to push me down by a value of 5 kilonewtons for each meter. So I'll go 1, then 5, another 5, another 5, because I'm going 3 times. So I'll get to the value of 1.07. Between C and D, there are no forces, so I'll continue in a straight line. Now the 20 will push me down, so I'll get to negative 18.93. I was at positive 1.07, and I was pushed down by 20 units, so I'll get to 18.93. Then between D and E, there are no forces, so I'll get to a straight line like that. Then the reaction EY, which is 28.9, will push me upward, and it will get me to 10. And there are nothing between here and here, between E and F, there are no forces, so I'll go straight. Then the 10 will push me down, closing the moment diagram. So what I have here is a straight line, then pushed up, then all the way to here, and this one's going down, and this one is pushed up. So this is the shear diagram. Now, what is the moment diagram? Okay, so I continue with the lines. Like that. And okay, let's do the moment diagram with the green. So the moment here is 0 because it's a free end. What is the moment at this point? It's the area of this, which is 1/2 times 10 times 2, which is minus 10. It's going to be here, minus 10. And this one is concaved this way. It's not a straight line, it's a second order. Okay, what about the moment at this point? Basically, it's the area of this part plus the area of this part, or the area of this part plus the moment value I got here. So what is the area of this part? It's trapezoidal, so I'll probably do it in blue in here. The area, let's call this A2. A2 should equal to 16.07 plus 1.07, taking the average of these two heights, this height and this height, and then multiply it by this base, which is 3. And I'll add it to the negative 10, which is the moment value before. And from that, I'll get a value of 15.71. So the value here is 15.71. Okay, now what is the value of the moment at this point? Add this area to this moment. The area of this is 1.07, which is the height, multiplied by this distance, which is 2, and add it to the 15.7. So you will get 17. Here, let's say it's 17.85. And let me clean this up for a second. It's 15.71. Now, what is the moment at this point? Again, add this area to the previous moment. This area right here is negative 18.93 multiplied by 2, which is this distance, and that will give me a value, plus I forget to add the 17.85, and that should get me a value of minus 20. So the moment here is minus 20, so let's say it's here, minus 20. Or let me just write it a little bit up higher so I can see it, guys. Minus 20. And the moment at the end, since it's free end, is 0. So I'm having a curve that goes like this. Or the curve will go just here. Then, starting from this point all the way to the end, they are all straight lines. Why is that? Look at the shear diagram. The shear diagram is decreasing and increasing, or decreasing or increasing, so it's not straight line. Whenever it's decreasing or increasing, the moment should be parabolic, and whenever it's a straight line like that, the moment should be a straight line, but increasing or decreasing depending on the values. Alright, so it's parabolic here, but starting from this point should be a straight line like that, and like that, and like that. Just be careful about this point here. Try to draw it like with, straight, with the corners, fine. Okay, from this graph we see something interesting. Let me push this up and to the right. The interesting points are this one and that one. These are the two locations the moment diagram is crossing the x-axis. So just a quick reminder, if this was concrete, where would you put the positive reinforcements or the bottom reinforcement and the negative reinforcements or the top reinforcements? So you need to find these two and say whatever's here is up and whatever is here is up, and for this I'll put the reinforcement in the bottom. So, but you need to know the distance. You're gonna tell the people at the site where to cut the rebars. So we have a mission of finding 2 points. And how do we find them? Again, simply by studying the shear diagram. So let me draw the shear diagram again so we will understand what's going on. Well, let me push this up. Okay. Now, let's see the shear diagram. So let's do it in red. The shear diagram looks something like this, and it has something like that. Something like that. That's the shear diagram I'm interested in. Okay, why did I do this segment only? Because this segment, if you look at the shear diagram from the problem, this segment includes the 0 moment point. So what I'm trying to find now, I'm trying to equate 2 areas. The areas I'm trying to equate is this area with some area here, and if I set these two equal, I can find the distance x from this point to this point where the moment is 0. How do I find this? It's not as easy as we've done it before. Okay, so let's put some numbers here. I have a minus 10, I have 1.07, and at the top I have 16.07. The way to do this part is a little bit tricky, but bear with me. We understand now that I have to equate 1 and 2, but the problem is I need these two distances, not only one distance, which used to be this one. Now I need the height y and the distance x. How do you know the height y? Okay, if you know the equation of this line, y equals mx plus b, you can get the coordinates of this point, x and y. So let's start by doing this. Let's try to find the y equals mx plus b. And the 2 points I'm going to study are these. Okay, what are the coordinates of this point? The coordinates of these points are 0 and 16.07, and this one is 3 and 1.07. These are the 2 points. So from these 2 points I can find the b value with the y-intercept, and I can find the slope. How to do this? Very quickly. Whenever y is 0, the b is the y-intercept. So look at this first point. Whenever the x is 0, b is the y-intercept. So x is 0 here, so the b should be equal to this part. Okay, so b already found to be 16.07. Now substitute the other point to find m, for example, or you can do m can be y2 minus y1 over x2 minus x1, or you can simply substitute the second point into the equation. So if I substitute the second point into the equation, the y for the second point is this, equals to m multiplied by 3, which is the x, plus 16.07, and if I solve for the m value, I will get a slope of minus 5. So the equation for my line is y equals, let me write it here, y equals minus 5 x plus 16.07. Okay, now let me clean up this area to make some room. I don't want to move this up again. So let's see, we have the equation now, we don't need all of this. Okay, no, okay, this one is minus 10. Alright, now I need to equate the two areas. Let's equate the two areas. So A1 equals A2. That's what I want. So what is the area here? It's 1/2 multiplied by 2, which is this distance, multiplied by -10, should equal to, what is the area of this trapezoid? The unknown trapezoid, this one. It is the 16.07, this height, plus this height. This height is y. I don't know this height yet. Y. I'm taking the average divided by 2, then multiplying it by x, which is the base. Now I have y and x in this equation, but I know how to I know how to represent y in terms of x using this equation, because y equals minus 5x plus 16.07. So what I need to do now is just to rewrite this equation knowing the following. So the area of this is minus 10 equals 16.07 plus what is y? It's minus 5x plus 16.07 over 2, the whole thing multiplied by x. Now what I need to do is just to simplify this. Okay, and how do I simplify these two? And by the way, I don't need to include this minus sign because I'm equating. If I'm saying that area 1 plus area 2 equals to 0, yeah, then area 1 equals negative area 2, so there is a minus sign here. But I'm equating these two, so there is no need for this minus sign here. So basically the area is just 10. If I expand this, I'll get the following. I can take the 2 multiplied by the 10, and I can add this one to that one, and then the whole thing is multiplied by x. I will get the following. After some algebra, I'll get x squared minus 6 4 2 8 x plus 4 equals to 0. So I have an equation. I need to solve for x. If I solve for x, just use your method. Use a computer, a calculator, whatever you want. If you solve for x, you'll get two values. X equals 5.73 meters, or x equals 0.69 meters. Now let's take a look back at, okay, look at these numbers. Let's try to take a look at the distance x we're trying to find. X, let me push this a little bit up so you know. X is this distance. Now if this is x, can it be 5.73 meters? Of course not, because the whole length here, I believe it was 3. So by inspection this value fails, and this should be x. Now you know the first point where the moment is 0.69 from the left support, or you can simply say it's this distance, 0.69 meters, or from here this distance is 2.69 meters. And for the second one, I'll leave it for you guys as an exercise. You come up with a number and just tell me what you get, but it's way simpler than this, because if you're trying to equate two areas, you're gonna have two triangles here, so it's similar to the one we've done in the first example. Okay, I know that was a long tutorial, but I hope that I answered the question about the importance of the zero location, of the zero moment location, and how can we get that using our quick way of writing, or our quick way of finding the moment diagram and the shear diagram. And remember, there is another way, which is finding the equation of the moment diagram and setting that equation equal to 0 and then solving for x. So whichever you think is easiest for you, just go for it, and I'll hope all you guys got the main idea here. Right? See you in future tutorials.